So ये कहाँ गया? Not this file. Okay. So we have been discussing quantum mechanics, the different postulates, and there was a question about the last class that we were trying to yeah. So when it is if a wave, if a particle is expressed by these three functions superposed for each other, such that the overall function is this wave function, then what will be the energy? So there will be three values of so one thing was clear, that there are three values of momentum, k1h cross, k2h cross, and k3h cross, that we will get for the three functions, and but which one we will get, that we can only talk about in terms of probability. So the coefficients that we see, square of this is their probability. So 3 by 8, 3 by 8, and 1 by 4. So this is the three probability that we will get. So the probability of getting k1h plus k1h cross is 3 by 8. Probability of getting getting this plus k2h cross will be 1 by 4, and getting plus k3h cross will be 3 by 8. So that means out of 8 measurements, 3 plus 3 plus 2, that is how you are getting. Okay, 3 plus 2 plus 3, whatever you can say. So 3 times this, 2 times that, that is the idea we are getting. So once you have known the momentum, you can also, suppose when you try to measure the energy, it is in the same measurement you will try to do this. So if your momentum is known, you can determine the energy. So you can, with the energy also, you will have that situation, that if when you are getting plus k1h cross, at that time the energy is kh square by 2m in this, so k2 square by h cross square by 2m, and third like that, k3 square h cross square by 2m, and with the same probability 3 by 8, because if the value of momentum is this, the same, simply square it and divide it by 2m, momentum square divided by 2m, with the same probability you will get the value of energy. Contrast it, इसके साथ आप contrast कीजिए जो पहले example हमने discuss किया था. There was one more example that we had discussed, cos kx वाला. If you can contrast it with this, the superposition, थोड़ा आगे निकल गया, slide number, yes, this one. So you can contrast this with this. Here also we had used superposition of two waves to explain cos kx, but here both we were getting plus k1h cross or minus kh cross, and both of them were equally probable. So if I am making 100 measurements, out of that 50% were kh plus kh cross, 50% minus kh cross. But if you calculate energy in both cases, the energy was k square h cross square by 2m. So you are absolutely certain about the energy in this case. ठीक है? But you are yeah. So that is the case. So from different types of wave function, different types of profile, we can derive this kind of information, that what we are knowing with certainty. So you are 100% certain what is the energy. You were also certain about the magnitude of the momentum, but the direction was like 50-50. You were getting plus k1 plus x direction one time, and minus x in the next time. So out of any large set of measurements, you will have 50% probability of finding that way. So in this case, you were having clear, the energy was known with certainty, that if a measurement is performed, you will get plus x for both the things. The energy will be same, whether it is moving in plus x direction or whether it is moving in the minus x direction. The energy was k square h cross by 2m. So these kind of the things, you have to interpretation of the things would be like this, the way we have talking. So this is the one thing. And then we had discussed the expectation value to. So expectation value, when we superposition we have talked about, and this important term that was expectation value, that is a way of taking the averages in quantum mechanics. So it is defined like this. And we have talked about how it is it was always so the operator, the I if average value of omega, if it is a normalized wave function, then expectation value is going to be a constant value like this. It is omega. So this was the if it is eigenvalue equation, eigenvalue function, if psi is the eigenfunction, then every measurement observable will yield a value, eigenvalue omega. So these are things that we had done already. So okay, and we also talked about this orthogonality of the things, where we proved that the theorem where if the for the same operator, if you have two eigenfunctions, then if the product, their product should be 0 over all space, and if you with the product and then take the integral, that should be 0. So this is what we describe mathematically, like writing like this. So practically if you are plotting graph, then it also means you have to take area under the curve, जहाँ पे दोनों function cross करेगा. अच्छा, वो example शायद मैंने slide में include नहीं किया है. But practically orthogonality will mean when you have so the area under the curve should turn out to be 0 if the two functions are plotted together. Yeah, I should have included that one. इंटीग्रेशन जस्ट लाइक व्हेन यू डिफरेंशिएट, इट इज द डिफरेंशिएशन क्या होता है जब आप स्लोप लेते हो dy by dx. इंटीग्रेशन क्या होता है जब ग्राफिकली इट इज डिस्क्राइब्ड एज you plot two functions y and x, and you take the area under the curve, that is integration. So graphical way of differentiation and integration, that also you should know. In fact, in practicals I will tell you. In practicals you will be doing a lot of them. Your seniors have just done in the second semester also, physical chemistry things. And so how to integrate and differentiate graphically. Okay, so if so this function orthogonality was discussed, the theorem was discussed by applying the principles, the way we are developing the concepts, and then we applying one by one, and then applying the concept of Hermitsky, we got some two results. So the idea was simple, how to get the orthogonality. To prove the theorem of orthogonality, we had taken two functions of I psi and j, psi j, as to be an eigenfunction, two different eigenfunctions for operator capital omega. So both satisfy these functions, and then we've solved them individually like this, reach up to this. So this is taking one side and taking its integral in this manner. You can when we try to calculate, so multiply them and integrate over all space. So this function is equal to omega I psi I. This is equal to omega I psi I. So this is what we have done, and we right hand side we are writing this, taking omega I, which is a constant term outside the integral, and then further taking the complex conjugate of the same, we can write both sides. We are taking the complex conjugate, and we reach to this situation, psi j psi I. So this can be further written like this. So this is just the same thing that we have written over here, multiplication, simple multiplication of the two terms. And if a similar way we try with this, we can reach this kind of equation, but the constant term over here is omega j. Here it was omega I. So this is our equation 1, and from this we applied in a second way of doing this was getting to the same thing, was applying the concept of hermiticity, and you got the results as equation 2. So if they satisfy, so if you interchange the positions and take the complex conjugate, it should be same as this. So that is the concept we applied, and that gave us this kind of value. So equation 1 and 2 both are, so this is right hand side of this equation 1 and 2 are same, and both must be equal. So that is what we compared the two and subtracted, getting this thing. So this term cannot be 0, so other term has to be 0. So this is how we prove this theorem of that any two eigenfunction of the same operator must be orthogonal. That is, the integral of their product should be 0. Okay, and then expectation value was something. So it was, as a general theorem, it was also said that this ck square, if you have if a wave function is to be expressed as a summation of a large number of waves, such that so ck is the number which is variable, omega k, so each way ck is the coefficient of that, then summation of this you have to take the summation of the ck square mod, only the modulus, so you don't positive negative doesn't matter, just this thing, square of that multiplied by the respective eigen values. So when you multiply this, that's the value, you get the expectation value. What is this? This is the expectation value. So symbol of expectation value is to be written like this in this bracket. So it is we say that it is a statistically weighted coefficient. Weighted coefficient मतलब हम उसका जो relative contribution एक एक wave का होगा वो सब जोड़ के देख रहे हैं, and ये statistically weighted coefficients. We also call it as a statistical weight, कि इतना % इसका contribution है, इसका इतना है, तो उसी proportion में वो reflect होगा final जो expectation value जो आप calculate करेंगे. So it is the modulus of the square modulus of the coefficient expansion coefficient that is coming into there in the picture. So this is the basis of postulate 5. This was the proof was done in a simple way. We simply suppose that it is C2 omega 2 C1 psi 1 plus C2 omega 2. Let's it be a sum of only two functions, not many, and then try to calculate, expand the terms